Hello, and welcome to the Chemistry Solution. This tutorial is on calculating enthalpies of reaction using bond enthalpies. A bond enthalpy is the amount of energy required to break a bond between two atoms in a gaseous compound, and it's often given in kilojoules per mole. Something that's important to remember is that the breaking of bonds always requires energy, and it's typically the formation of bonds that releases energy. So one way that you can calculate the enthalpy change for a reaction is by taking the sum of the bond enthalpies of the bonds broken and subtracting the sum of the bond enthalpies of the bonds formed. And in this equation, N and M stand for the number of moles of each type of bond. So let's try an example. Calculate delta H for the following reaction using average bond enthalpies and assuming all compounds are in their gaseous states. Remember that to calculate delta H for the reaction, we need to take the sum of the bond enthalpies of the bonds broken and subtract the sum of the bond enthalpies of the bonds formed. And remember that N and M pertain to the number of moles of each type of bond, so the first thing you need to do is to draw out the molecules so that you can see what different types of bond you have in your compounds. And now to keep track of all the types of bonds and how many you have, I think it's nice to set up a little chart where you have the bonds broken and the bonds formed. So let's start with the bonds broken. The first type of bond you'll see on your reactant side is the carbon-hydrogen bond. And you'll notice that we have 1, 2, 3, 4 carbon-hydrogen bonds. When we look on our table of average bond enthalpies, we'll see that to break 1 mole of carbon-hydrogen bonds requires 413 kilojoules. And we multiply this value by the number of moles of these bonds on the reactant side, which is 4. And then we multiply this value times the number of moles of this type of bond on the reactant side. The next type of bond we have is an O2 bond. And what you'll notice is that on average bond enthalpy tables, instead of listing the bond between O2, you'll just see O2 listed as a molecule. And that's because you sometimes see the structure of O2 represented differently, whether you're drawing a Lewis structure or whether you're using molecular orbital theory. And so most of the time, instead of drawing out the bond between two oxygen atoms in an O2 molecule, you'll just see the molecule O2 listed by itself on an average bond enthalpy table. Now the coefficient in front of O2 tells us that we have 2 moles of O2. And the average bond enthalpy to break the bond in a molecule of O2 is 495 kilojoules per mole. Now let's look at the bonds formed, and those would be the bonds on the reactant side. So you can kind of look at reactions as though you're breaking all the bonds on your reactant side in order to form individual atoms and then forming new bonds on your product side. So on the product side, we have a carbon-oxygen double bond. And we see that we have 2 different carbon-oxygen double bonds. And the average bond enthalpy for a carbon-oxygen double bond is 799 kilojoules per mole. The other type of bond we have on the product side is an oxygen-hydrogen bond. And we have 2 moles of water being formed. So it might be helpful to draw out your 2 water molecules like this. Now you can easily count up the oxygen-hydrogen bonds and see that you have 1, 2, 3, 4. You also could count up the oxygen-hydrogen bonds in the single molecule of water and multiply that by the coefficient in front of the water molecule in your balanced chemical equation. And the average bond enthalpy for an oxygen-hydrogen single bond is 463 kilojoules per mole. Setting up a chart like this makes it very easy to keep track of the number and types of the different bonds you have on the reactants and the product side. And now we can easily plug these numbers into our equation. So remember, we're going to sum up the bond enthalpies of the bonds broken and subtract from that the sum of the bond enthalpies of the bonds formed. I think it's helpful to write out this equation doing your math step by step so you keep track of negative signs and parentheses. This gives us a delta H value for this reaction of negative 808 kilojoules per mole. Let's try another example. Calculate delta H for the following reaction using average bond enthalpies and assuming all compounds are in their gaseous states. Again, the first thing you need to do is to draw out the structures of each of the molecules. Sometimes the structures of the molecules will be given to you, and sometimes you'll have to draw them yourself using your knowledge of drawing Lewis structures. Then we can set up our chart again, keeping track of the bonds broken and the bonds formed. When I look at the reactant side, I see that I have carbon-hydrogen single bonds, and I have 2 of them. And then I multiply that by the average bond enthalpy for a carbon-hydrogen single bond. I also have a carbon-carbon triple bond, only 1 of those, and I multiply that by the average bond enthalpy for a carbon-carbon triple bond. I also have 1 mole of hydrogen-chlorine bonds. And again, I multiply that by the average bond enthalpy for a hydrogen-chlorine single bond. Now let's look at the bonds formed. In this case, we had carbon-hydrogen bonds broken on the reactant side, and we have carbon-hydrogen bonds formed on the product side, 1, 2, 3 moles of them, multiplied by the average bond enthalpy for a carbon-hydrogen single bond. I have 1 carbon-carbon double bond, multiplied by the average bond enthalpy for a carbon-carbon double bond, and 1 carbon-chlorine bond, multiplied by the average bond enthalpy for a carbon-chlorine single bond. Now you'll notice that I have carbon-hydrogen bonds broken and carbon-hydrogen bonds formed. And so it's okay to look at the difference between the bonds broken and the bonds formed if you'd like. However, I think it's much easier, and you're going to make a lot less mistakes if you just count up all of the bonds broken and count up all of the bonds formed and subtract. So now we can plug these numbers into our equation. I sum up the bond enthalpies for all of the bonds broken and subtract the bond enthalpies for all of the bonds formed. This gives me a delta H for this reaction of negative 85 kilojoules per mole. Thanks for watching the chemistry solution. I hope you enjoyed this tutorial.